This is my trigonometry course. Today we're going to learn the basic trigonometric identities. If you haven't done the homework completely and correctly from last class, do that homework before watching this video. We first need to learn some general operations, some basic operations with trigonometric functions. The algebra with trigonometry works the same as you would expect with your basic x and y variables. So if we have 3 sine thetas and we're adding 5 sine thetas, we get 8 sine thetas. So it's just what you would expect. If we have 37 cotangent a's and we subtract 20 cotangent a's, then we have 17 cotangent a's. So this is just demonstrating that the algebra works as you'd expect it. It would. Go ahead and try number 3. When you come back, we'll do it together. Okay, we're back. 1 cosine beta plus 1 cosine beta is 2 cosine betas. And negative 9 secant b's plus 2 secant b's is negative 7 secant b's. So again, it's exactly what you would expect. So we added and subtracted trigonometric functions. Now we're going to multiply as you would expect. But it's very important to understand that when you multiply a trigonometric function by itself, we do not write sine theta squared. That's not correct. Because this notation means sine of theta times theta. That's what this means. And that's not what we're doing. We're not multiplying the angle by itself. We're multiplying the entire sine function by itself. So when you multiply sine by itself, you can either use parentheses or you can write the exponent to the left of the angle theta. Now, we never really write it this way because mathematicians and scientists and engineers, they don't really want to write those parentheses if they don't have to. So to get rid of those parentheses, we write it in this form. So just be aware, when you see this notation, it means sine theta times itself. And I know that this is very strange. Students don't like that, but you're going to have to get used to it because you're going to see that many times throughout your math curriculum. So let's try some practice problems. Cosine A times cosine A is cosine squared A. And notice I put the exponent to the left of A. Now we have tangent squared beta times tangent cubed beta. And remember exponent rule number 1 from my intermediate algebra course. We just add the exponents, so we get tangent to the 5th power beta. So go ahead and try number 7, and when you come back, we'll do it together. Okay, we're back. So if you got that answer, good job. Go ahead and try number 8. When you come back, we'll do it together. All right, we're back. If you got that one right, good. We added 8 and 3 to get 11, cotangent to 11th power b. Okay, so we added and subtracted trigonometric functions and we multiplied. Now, as you would expect, we're going to divide. And when we divide, we use exponent rule number 2. When you divide power expressions, assuming the bases are the same, remember we have to have the same base, x. In this case, the base is secant alpha. We just subtract the exponents. So 10 minus 4 is 6. So we have secant to the 6th power alpha. And sine to the 5th power over sine to the 3rd power, or sine to the 3rd power theta, is sine squared theta. Okay, so now it's time for you to try attempt number 11. When you come back, we'll do it together. All right, we're back. So 9 minus 6 is 3. And if you got that one right, good. Try number 12, and when you come back, we'll do it together. All right, we're back. If you got cosecant y, you're correct. You don't have to write cosecant to the 1 power. All right, so that was just some basic instruction on how to work with those trigonometric functions using elementary algebra. Now we're going to learn the purpose of this class, which is to understand the basic trigonometric identities. And these identities are so important, you're going to use them throughout your entire math education. You're going to see them all over the place in calculus and math analysis, also known as pre-calculus. You have to memorize these identities. You must know them by heart. And so there are two purposes of this class today. Number one, I'm going to help you to memorize these identities. And number two, we're going to see the types of problems that you may experience with these identities. Now, you might be wondering, why are these called identities? Well, that's just a fancy word that mathematicians came up to name these. They're just a bunch of equations. You could easily just say the basic trigonometric equations, but they use that fancy word identities. So I want you to get a screenshot of these identities or a picture with your phone. We can't constantly go back and look at these over and over and over again, so you need to have these right in front of you. Now, if you don't have the ability to take a picture, you can go online and just type in trigonometric identities. You'll find a list of all these. So again, I'm going to give you one more chance here to take a picture with your phone. You're going to need these right in front of you as we go along in the class today. Now, you might be wondering why these identities are true. For example, our reciprocal identities. Why is this true? Well, it's pretty easy to show why it's true. You're not going to be required to explain, so you don't really need to prove the identities, but I just want to give you an idea of why these things are true. So let's look at the first reciprocal identity. There's 6 reciprocal identities. That's the green ones up there. So why is this true? Well, these 6 trigonometric functions refer to right triangles. And if we call the side adjacent theta x and the side opposite y and the hypotenuse r, then sine theta is equal to y over r. That's just what it is. That's just the definition. Cosecant theta is equal to r over y. Again, that's just what it is. That's the definition. If you simplify this expression here, and you can do it in many different ways. I'm using the old school division symbol. Remember, a fraction symbol can be considered division. A fraction is a division operation. And you simplify, you can prove pretty easily that this equation works. So we're starting by assuming that the equation is true, and then we're proving if that is true, this should work out, and it does. This is one of the ratio identities. There's 2 ratio identities. And again, you can use a similar proof. Tangent theta is defined as y over x. That's just what it is. Sine is y over r. Cosine is x over r. And if you simplify this expression, you get y over x. That proves that it's true. So again, you don't have to know these proofs. I'm just giving you an idea of why they work. We're not going to spend a lot of time on this. Now, let's assume that this is true and show that it is. Again, sine is defined as y over r. Cosine is defined as x over r. Again, using this triangle. So if you do the math, use exponent rule number 4. Maybe I should write that. That is exponent rule 4 from my intermediate algebra course. Now, if you didn't take my intermediate algebra course, you should still know these basic rules, but if you want to refer back to my course, That's rule number 4, which tells us that x over y to the a is equal to x to the a over y to the a. And I should probably use different variables so I don't confuse you. Let's use m and n. So again, that demonstrates the exponent rule number 4. So we use that going from here to here. Again, this is not what this class is about. I'm just quickly showing you why these rules work. So now we have two fractions with the same denominator. We add them up, combine them, and look at this here. That's the Pythagorean theorem. Remember, a squared plus b squared is equal to c squared. Well, now we have x, y, and r, so x squared plus y squared is equal to r squared. So the x squared plus y squared now equals r squared, and r squared over r squared is 1. So if you want to look at these, you can. We're not going to spend much time proving those. In fact, we're not going to spend any time. I just wanted to give you an idea of why those identities work. Very easy to show why they work. So now we're going to start with the important part of this class. We're going to do a lot of problems showing how to simplify expressions using these identities. And again, we're going to accomplish two things. I'm going to force you to memorize these identities. You must memorize them. And we're going to do a lot of problems. And the purpose for these problems is to force you to memorize the identities. So we're going to start with expressions that require the reciprocal identities. Those are the green identities over here. We're going to use these green ones to simplify these expressions. And we're going to start with very easy problems. These may be a little easy for people who have already seen a little trigonometry. For those people, I apologize that this is a little easy, but we need to start easy. There's no reason to start with hard problems. Okay, so I can change this function or this function. It doesn't matter, but typically we want to change a cosecant function to a sine rather than a sine to a cosecant. So I changed the cosecant theta to 1 over sine theta. How is it that I'm allowed to do that? I'm allowed to do that because our reciprocal identities. Now, you don't have to write a dot here or parentheses if you don't want to, but you can. So now we're going to multiply, and you can consider this sine theta to be sine theta over 1, and you're just multiplying fractions. So by now you should know how to multiply fractions. You just multiply the numerators. Sine theta times 1 is sine theta. And again, 1 times sine theta is sine theta. This is very basic algebra. So sine theta times 1 is sine theta. And 1 times sine theta is sine theta. Very, very basic algebra. I apologize again to those people who know this pretty well. Now, you don't have to show this step. Once you get to this step, you can just write the answer. But again, I'm going very slow here so that you can see exactly what's happening. But we're going to speed up as we go along in the class because I don't want to bore you. So we took this expression and we simplified it. If we can write that expression as 1, then why would we keep it as sine theta times cosecant theta? All right, let's try another example. Let's convert cotangent omega to 1 over tangent omega. And again, you can just make this 1 immediately. You don't have to show this intermediate step. But I'm going to go ahead and show the intermediate step. When you multiply 1 over tangent omega and tangent omega, you get tangent omega over tangent omega, which is 1. And 1 minus 1 is 0. So it turns out that that entire expression simplified to 0. Okay, so I'm going to give you one more chance to take a picture of these reciprocal identities. And I want you to try number 15. And when you come back, we'll do it together. Okay, we're back. So you can change cosine to secant or secant to cosine. There's two different ways to do it, but I'm going to change secant to 1 over cosine. So I took this secant and changed it to that. And when you multiply these two expressions, you get 1. Again, you don't have to show that step. So if you got that answer, good job. Try number 16. When you come back, we'll do it together. Okay, we're back. So we have 2 minus tangent omega times 1 over, did I say omega? I meant beta. When you multiply those two, you get 1, and so we're left with 1. If you got that answer, excellent, perfect. Again, we're starting with very simple problems. There's no reason to start with complicated problems. Okay, so let's try this next problem. Cosecant is 1 over sine A. Now, you don't have to show this next step that I'm about to show, but I just want to make it clear. When you multiply these yellow expressions, these highlighted expressions, you get sine A over sine A. You don't have to show that step, but I'm just trying to explain what happens here. They just cancel out. This is just equal to 1. And I don't really have enough room to even show that, so I'm not going to show that intermediate step. The yellow numbers, they cancel out. You're left with cosine A, and 2 cosine A plus cosine A is 3 cosine A. So that is the final answer. So look at this complicated expression up here. This complicated expression simplified all the way to 3 cosine A. So that's why this math is very important. When you take upper math courses, you're going to be expected to simplify trigonometric expressions. Let's try number 18. I'm going to convert cotangent alpha to 1 over tangent alpha. There may be some different ways to do these problems. If you try a different way and it doesn't work, that's okay. You can just try things and see what happens. So 1 over tangent alpha times tangent alpha cancels out those terms, and we're left with secant alpha minus secant alpha. And as you can imagine, that is 0. So go ahead and try number 19. And when you come back, we'll do it together. Okay, we're back. So I'm going to change, there's more than one way to do this, but I'm going to change secant B to 1 over cosine B. And these highlighted terms, they cancel out. So we're left with sine B minus 3 sine B, which is, of course, negative 2 sine B. So if you got that one right, excellent. Very good. If you made a mistake, that's okay. Just go back and figure out what you did wrong. Go ahead and try number 20, and when you come back, we'll do it together. Okay, I'm going to rewrite 5 cosecant omega, and cotangent omega I'm going to rewrite as 1 over tangent omega. And again, as you can see, the tangents just cancel out, because we have a tangent in the bottom and technically a tangent in the top if you consider this to be a fraction, tangent omega over 1. So we're left with 5 cosecant omega plus cosecant omega is 6 cosecant omega. All right, so if you got that right, good. Okay, so now we're going to be going in the opposite direction, so to speak. We're still using reciprocal identities, but we're going in the opposite direction. So we have a fraction, and we're going to actually convert it to something that doesn't look like a fraction. So I'm converting both of those tangent betas, 1 over tangent betas, to cotangent betas. That is one of the reciprocal identities. And the reason that I'm doing that is I'm getting rid of the fractions. We don't really like fractions. We don't prefer fractions. If we can avoid them, we want to. So you probably agree that this expression is much simpler than this expression. Okay, let's try another one. Now, to make things a little easier to understand, I'm going to factor out that 3. Isn't it true that I can write this expression like that? I'm hoping that this is going to make it easier for you to see. We just factored out the 3 and the 2. And 1 over cosine is equal to secant theta. Look at your reciprocal identities. And 3 secant theta minus 2 secant theta is 1 secant theta. So there you go. So that expression simplified to this. So now it's time for you to try. Go ahead and attempt number 23. Again, you should have those reciprocal identities right in front of you. Try 23. When you come back, we'll do it together. Okay, we're back. So we get cosecant omega plus cosecant omega plus cosecant omega. These problems are very easy, as you can see. There's no tricks here. We're not trying to trick you. Okay, if you got that right, good job. If you're having a little trouble with these, that's okay, because you're starting to get used to them. Even if you're having a little trouble, notice that you're starting to understand what's going on here. That's the key. Try number 24, and when you come back, we'll do it together. Okay, we're back. So you don't really have to factor the 5 out. I could factor out 5, and then we have 1 over cosine alpha, right? Then we can change the 1 over cosine alpha to secant, and then it becomes 5 secant. But you don't really have to show that. We can just bring the cosine up, and it becomes 5 secant alpha. And we get 8 secant alpha and negative 2 secant alpha. Alright, so now we just combine like terms. 5 secant alphas plus 8 secant alphas is 13 secant alphas, and then minus 2 gives us 11 secant alphas. If you got that one right, excellent. Okay, so again, we're only using the reciprocal identities. We're not using the ratio identities or the Pythagorean identities. We're starting slow here. So now we have 1 over cosine squared a, and I'm going to change that to 1 over cosine a times 1 over cosine a. All I did was just change the form of that expression. That's all I did. Isn't it true that if you multiply the yellow and the green expressions, you get 1 over cosine squared a? Because when you multiply fractions, you multiply the numerators. 1 times 1 is 1. And the denominators, cosine a times cosine a is cosine squared a. So I factored. Remember, the word factor basically means to go backwards in a sense. Instead of multiplying, you're going in the opposite direction. The reason that I did that is because the green reciprocal identities tell us that 1 over cosine a is secant a, and 1 over, well, they're both secant a. So secant a times secant a is secant squared a, and there you go. All right. Now, you don't have to show this step, or any of these steps really, in these problems. You're going to get to the point where you're going to do these very, very quickly, so you don't have to show that. So in the next problem, for example, we have 1 over cosecant squared b. You know that 1 over cosecant b is equal to sine b, so we can just change that to sine squared b. That's perfectly fine. You can just jump right to the answer. Now, you're probably wondering, why do we have to do this? Why do we have to flip that and change it to sine squared b. Well, you're going to see that hundreds and hundreds and hundreds of times in upper mathematics courses, especially this course, but also pre-calculus. So you need to do that quickly. You need to get used to it. You may not like it, but you're going to get used to it. Go ahead and try number 27. When you come back, we'll do it together. All right, we're back. So 1 over tangent is secant, or excuse me, it's cotangent. So we just changed that to cosine or cotangent squared theta. If you got that right, good. Try number 28. When you come back, we'll do it together. Okay, we're back. So that's going to change to cosine squared theta. If you got that right, good. All right, on to number 29. So in the previous problems, we used the reciprocal identities to simplify expressions, but now we're going to use the ratio identities. So those are the orange identities that I gave you. So I want you to take a picture, if you haven't already done that, take a picture of these ratio identities. You're going to need these. If you don't have these in front of you, then you're going to have no clue what we're doing. Okay, so we have an expression here, and I'm going to change tangent to sine theta over cosine theta, because our ratio identities tell us we can do that. And if you multiply cosine theta by something over cosine theta, assuming that this cosine theta is a factor of the overall number in the denominator, then we can cancel those out. So I'm going to cancel out those cosine thetas, and we're left with sine theta. Now you can write an intermediate step if it makes you feel better when it comes to the math. When you multiply those, again, when you multiply something that looks like a whole number, you just write over 1, and you multiply as if they're fractions. If they're fractions, you multiply the numerators to get cosine theta, sine theta, and multiply the denominators to get cosine thetas. So now we have this expression here. And again, the cosine thetas cancel out. So you're left with sine theta. Again, you don't have to show this step here. I'm just going very slow for students who have never seen this before. So we simplified this expression to sine theta. That's much simpler. All right, let's try a problem that's a little harder. We have a fraction here, and I'm going to change. Well, maybe I should go ahead and just change that fraction symbol to a division symbol. Remember, the fraction symbol can be interpreted as a division operation. So now I'm going to use one of my ratio identities. Cotangent theta is equal to cosine theta over sine theta. And by the way, there's a lot of ways to do this. You may choose to do this a slightly different approach. So all we did was just change cotangent theta to cosine theta over sine theta. That's all we did. But now I'm actually going to divide. Remember, when you divide a fraction, you change the operation to multiplication, and you flip the divisor. So now we have sine theta over cosine theta. We did have cosine theta over sine, but now we're changing it to sine over cosine. So now when we multiply, and again, you don't have to show this, but when we multiply, these cosines cancel out because there's a cosine in the bottom, and we're multiplying by cosine, so we end up with sine theta. So you see that we really simplified that expression. We had a fraction, and now we don't have a fraction. And there's only one trigonometric expression rather than two, or one trigonometric function rather than two. So again, we're using the ratio identities. So let's try another problem. Now, this problem requires us to go in the opposite direction. In the previous problems, we were converting tangent to sine over cosine, or cotangent to cosine over sine, but now we're converting sine over cosine to tangent beta, because that just makes it more convenient to see what's happening here. And of course we get 0. Now again, a lot of students are going to think, this stuff is kind of easy. It's kind of boring. It's easy. But if you've never seen this stuff before, what's happening? What's happening is you're slowly starting to memorize these expressions, and we've only just begun. So if this is your first time with trigonometry, you need to do every single problem that I assign you, because every problem has a purpose. Okay, let's try one more of these. I'm going to convert. You can really do this in one step, but I'm going to convert that expression using exponent rule number 4 in my intermediate algebra course, if you want to go back and look at that. And we're going in the opposite direction. So we went from here to here. That's typically considered the opposite direction. The reason I did that is because our orange ratio identities tell us that sine A over cosine A is tangent A. So we have tangent A squared. So this here, that converted, maybe I should use orange because these are reciprocal, or the ratio identities. And of course we never write tangent squared as, we never write it with parentheses really, because we don't want to have to write the parentheses. Okay, so I want you to take a screenshot of these problems, because you're going to need these to help you do the next problems. Go ahead and try number 33. You should have your orange ratio identities right in front of you. I'm going to give you a chance to take a picture of those. You should have these right in front of you. And try number 33. When you come back, we'll do it together. All right, we're back. So I'm going to change cotangent theta to cosine theta over sine theta. And when you multiply these signs, they just cancel out. You're left with cosine theta. So if you got that right, excellent. All right, try number 34. When you come back, we'll do it together. All right, we're back. So I'm going to change that fraction symbol to a division operation. And I'm then going to change the tangent theta function to sine theta over cosine theta. How am I able to do that? Well, that's one of the ratio identities. I'm changing this to that. Okay, so now we're going to divide. When you divide a fraction, you change to multiplication and flip the divisor. And so you can see that the signs cancel out, and we're left with cosine theta. So if you got that right, excellent. Go ahead and try number 35, and when you come back, we'll do it together. All right, we're back. So now we're going in the opposite direction. Cosine omega over sine omega is cotangent omega. And you add those together, you get 2 cotangent omegas. So if you got that right, perfect. Go ahead and try number 36, and when you come back, we'll do it together. Okay, we're back. You really don't have to show any work here. You can just change that to cotangent squared A. You can do some intermediate steps if you want to, but you really don't have to. If you want to know why that's true, you can just go back to this problem. All right, so if you got those right, good job. Let's now move to the Pythagorean identities. Now these are going to be the purple identities that I showed you. So let's go look at those identities real quick. Take a picture if you have not seen these. If you don't have these right in front of you, then you're going to have a lot of trouble with the class today. Okay, so we're going to simplify this expression, but those purple Pythagorean identities tell us that sine squared plus cosine squared is equal to 1. So there you go. It's that simple. We simplified that expression to 0. So sine squared plus cosine squared is equal to 1. Let's try number 38. In number 38, we're kind of going backwards. We're going to let 1 equal sine squared theta plus cosine squared theta. There's an easier, or I should say there's a faster way to do this, but this is the easiest way to understand. So I changed that 1 to sine squared theta plus cosine squared theta. But now, look what happens. We're subtracting sine squared, so those sine squared thetas cancel out, and you're left with cosine squared theta. So 1 minus sine squared theta is equal to cosine squared theta. Why would we write 1 minus sine squared when we can simplify it to cosine squared? You're going to do this hundreds and hundreds of times in upper mathematics courses. So let's go to 39. If you look at your purple Pythagorean theorem, or Pythagorean identities, 1 plus cotangent squared beta is equal to cosecant squared beta. That's not beta, that's just b. And so now we're just going to use the exponent rules. Rule number 2. We're dividing powers, second power minus first power. So we just have cosecant to the first power, but obviously you're not going to write a 1 when we can just leave it like that. Okay, so now we're going to go in the opposite direction. We're going to change one trigonometric function to a sum. There's many different ways to do these problems, so if you're thinking that there's another way, you're right. There are many other ways, but we changed secant squared b to tangent squared b plus 1. There's 3 Pythagorean identities, and that is one of them. The reason we did that is because now these tangent squared b's cancel out, because this is a negative tangent squared b, this is a positive. So we're left with 1. That expression simplifies to 1. Now again, what are we doing here? What's the purpose of this? Well, we're doing 2 things. Number 1, we're demonstrating the type of problems that you're going to see when you use these identities. And the second thing we're doing is I'm forcing you to memorize these identities. You're seeing them over and over and over again. So take a picture of these problems at the right, and I want you to use those to do number 41. Attempt 41, and when you come back, we'll do it together. All right, we're back. So sine squared plus cosine squared is equal to 1. So there you go. Again, these problems are not hard. Go ahead and try number 42. When you come back, we'll do it together. All right, we're back. So 1 is equal to sine squared theta plus cosine squared theta. So that 1 changed to this. And notice that the cosine squareds cancel out. So 1 minus cosine squared theta is equal to sine squared theta. Go ahead and try number 43, and when you come back, we'll do it together. All right, we're back. So tangent squared omega plus 1 is equal to secant squared omega. So that numerator changed to secant squared omega. And secant squared divided by secant is just secant. Again, we used the exponent rule number 2. We just subtract the powers. Now this secant in the bottom doesn't have an exponent, but remember, if a number doesn't have an exponent, it's assumed to be 1. That's exponent rule number 6 from my intermediate algebra course. Okay, on to number 44. Go and attempt number 44. When you come back, we'll do it together. All right, we're back. We're going to replace cosecant squared with 1 plus cotangent squared. And you can see why we did that. The cotangents are going to cancel out, and we're just left with 1 plus 1, which is 2. So that expression simplified to 2. So if you got that one right, excellent. Okay, let's go on to another problem here demonstrating the Pythagorean identities. Now we're multiplying two binomials. We've got a binomial here and a binomial here. And binomial just means there's two terms, here and here. You could call this a trigonometric binomial. So what we're going to do is we're going to use an acronym, FOIL. And you should be very familiar with this operation. But if you have not seen it, we're going to demonstrate how this works. We're going to multiply the first terms. F stands for first terms. The first terms are 1 and 1. 1 is the first term in the first binomial, and 1 is the first term in the second binomial. So we're going to multiply those together, and we get 1 times 1. Now again, this is very simple stuff for students that have seen this already, but if you have not, then we're gonna demonstrate this. So now, O stands for outside terms. We're going to multiply the outside terms. These yellow terms here are the outside terms. So we're going to multiply 1 and negative sine omega. So we get 1 times negative sine omega. Again, that's the outside terms we're multiplying. And notice that we're adding all the terms up after we multiply. So now we're going to multiply the inside terms. So let me get another highlighter for that. We can use maybe purple. We're going to multiply the inside terms. That's these terms here, sine omega times 1. All right, so then we're going to multiply the last terms. And let me find another highlighter for that. Maybe we should color this, we'll color it pink, I guess. I'm running out of colors. So L is the last terms. We're going to multiply this term by this term. So we have sine omega times negative sine omega. We multiplied the last terms. And so we have 1 times 1 is 1. 1 times negative sine omega is negative sine omega. And 1 times sine omega is sine omega. And sine omega times negative sine omega is negative sine squared omega. So we're just doing all the operations that we demonstrated in the first part of this class. The only difference here is we're using parentheses. Okay, these cancel out, and you're left with 1 minus sine squared omega. But if we use a Pythagorean identity, remember, 1 is equal to sine squared omega plus cosine squared omega. So we used a Pythagorean identity, and you can see that the sine squareds cancel out, and you're left with cosine squared omega. So who knew that this expression up here was going to simplify all the way to cosine squared? But it did. In calculus, again, you're going to be expected to be able to do this. So you can take a picture of FOIL there to help you. So we're going to multiply the first term. Secant beta times secant beta is secant squared beta. The outside term, secant beta times -1, is negative secant beta. And the inside terms, 1 times secant beta is secant beta. And the outside terms, 1 times -1 is -1. The secant betas cancel out, as you can see, and you're left with secant squared beta minus 1. So now we can use a Pythagorean identity. Secant squared beta is equal to tangent squared beta minus 1. That's a Pythagorean identity. Excuse me, not minus 1. It's equal to tangent squared beta plus 1, and then we still have that minus 1 there. Alright, so as you can see, the 1's cancel out, and you're left with tangent squared beta. So again, we simplified that expression. Alright, so time for you to try. You're going to need to use FOIL. So I have FOIL up there. Go ahead and try 47. When you come back, we'll do it together. Okay, we're back. So f of FOIL tells us to multiply the first terms. Cosine alpha times 1 is cosine alpha. Then we're going to multiply the outside terms. That's O of FOIL. Cosine alpha times cosine alpha, well, negative cosine alpha, that is negative cosine squared alpha. Then we're going to multiply the inside terms. 1 times 1 is 1. And then we're going to multiply the outside terms. 1 times negative cosine alpha is negative cosine alpha. So now we're going to cancel out these terms because we have a negative cosine alpha and a positive cosine alpha. And then we're left with negative cosine squared alpha plus 1. But remember that 1 is equal to sine squared alpha plus cosine squared alpha. So you can see that we have a negative cosine squared and a positive cosine squared. They cancel out, and we're left with sine squared alpha. So there you go. This entire expression here is simplified to sine squared alpha. When you take a calculus course or a math analysis course, why would you write the expression in this way when you can simplify it to sine squared alpha? So you can take a picture of these problems if you want to help you do the next problem. I want you to try one more of these. Go ahead and try 48. When you come back, we'll do it together. Okay, we're back. Multiply cosecant x and cosecant x, and we get cosecant squared x. That's the first terms, and then multiply the outside terms. Cosecant x times 1 is cosecant x. Then multiply the inside terms. Negative 1 times cosecant x is negative cosecant x. And the outside, or the last terms, negative 1 times 1 is negative 1. The cosecant x's cancel out, and we're left with cosecant squared x minus 1. But we know that cosecant squared x is the same thing as 1 plus cotangent squared x. So I changed this expression to this using the Pythagorean identities. So the 1's cancel out, and we're left with cotangent squared x. And there you go. So, if you got that right, perfect. So, we used the reciprocal identities to simplify expressions, the ratio identities to simplify expressions, and the Pythagorean identities. Now we're going to start to combine those identities to simplify expressions. We're going to use the reciprocal and the ratio identities in these next problems. So if you look at your orange identities, you can see that sine over cosine is equal to tangent. So that was the ratio identity. But the reciprocal identities tell us that 1 over tangent theta is equal to cotangent theta. So there you go. So we used 2 of the identities. Let's try number 50. Secant is 1 over cosine. So that's a reciprocal identity. So I'm going to use green because that was a reciprocal identity. But now if we multiply using just basic arithmetic, you know that if you multiply a fraction by something that looks like a whole number, you just multiply the numerator by that thing. And so now we have sine b over cosine b, but you know that that is tangent b. That is one of the ratio identities. So I'm going to color that orange because that's a ratio identity. All right, so on to number 51. Let's try a couple more of these before you try one on your own. Again, we're using the ratio identities and the reciprocal identities. So cosine or cotangent is equal to cosine alpha over sine alpha. And secant, did I say alpha? I meant theta. Secant theta is 1 over cosine theta. So I used a ratio identity to change this into that, and I used a reciprocal identity to change that into this. Now I want you to notice something very important. We have a cosine on the top and a cosine on the bottom. And for all intents and purposes, this sign is on top because you can consider it to be a fraction. And this sign is on the bottom. So what that means is they all cancel out. So that one cancels out, that one cancels out, that one cancels out, and that one cancels out. When you multiply all those, you get 1. And 1 minus 1 is 0. So again, we used the ratio identities and the reciprocal identities. So let's try one more of these. Tangent theta is secant or sine theta over cosine theta, and cosecant theta is 1 over sine theta. So we used a reciprocal identity and we used a ratio identity. So we're going to multiply, and you see these signs, they cancel out. So we're left with 1 over cosine theta. And 1 over cosine theta, well, that's another reciprocal identity. So we get we get secant theta. So I want you to try number 53. We're using the ratio identities, the orange ratio identities, and the green reciprocal identities. Try 53, and when you come back, we'll do it together. Okay, we're back. So cosine A over sine A is the same thing as cotangent A. That's one of your orange ratio identities. 1 over cotangent A is equal to tangent A. That's one of your reciprocal identities. All right, that's the green ones. So if you got that right, good job. Go ahead and try 54, and when you come back, we'll do it together. All right, we're back. So cosecant A is 1 over sine A. That's one of the reciprocal identities. And when we multiply those together, we can combine to one fraction, cosine A over sine A, but you can recognize that as a ratio identity. So that's going to change to cotangent A, and that's the final answer. So if you got that right, excellent. Again, the purpose of this is to slowly memorize these identities and to see how they're used in example problems. So go ahead and try 55, and when you come back, we'll do it together. Okay, we're back. So tangent is equal to sine over cosine. You can see those cosines are going to cancel out. Cosecant theta is 1 over sine theta. And so we used a reciprocal identity and a ratio identity. The cosines cancel out, and the sines cancel out, and you're left with 1. So if you got that right, excellent. Okay, go ahead and try number 56, and when you come back, we'll do it together. All right, we're back. Cotangent theta is equal to cosine theta over sine theta, and secant theta is equal to 1 over sine theta. Whoops, that's not 1 over sine theta, sorry. That's 1 over cosine theta. There you go. So then we cancel out, cosines cancel out, and we end up with 1 over sine theta. Now the sine theta is still in the bottom. That doesn't magically flip to the top. So we then need to use a reciprocal identity again to convert to cosecant theta. So if you got that one right, perfect. Okay, so let's try number 57 together. We're still using the reciprocal identities and the ratio identities to solve, or just to simplify expressions. So let's change that fraction symbol to a division operation. Remember, we're allowed to do that. And tangent theta is equal to sine theta over, well actually before we, well I guess we can go ahead and convert. That's sine theta over cosine theta. And we're going to change secant theta to 1 over cosine theta. So we used a ratio identity and a reciprocal identity. So now, remember, when you're dividing a fraction, you change to multiplication and flip the divisor. So now, when you multiply, you're going to see that these cosines cancel out because there's 1 on top and 1 on the bottom. So we have sine theta over 1, but you don't really even need to write that because you know that the final answer is just going to be sine theta. All right. So let's try one more of these. Before you try one on your own, we're going to convert that fraction symbol to a division symbol. And we're then going to use the reciprocal identities. So we have 1 over cosine y divided by 1 over sine y. And when you divide fractions, you change to multiplication and flip the divisor. When you multiply those, 1 times sine y is sine y, and 1 times cosine y is cosine y, and you may recognize that. That's a ratio identity. Sine y over cosine y is equal to tangent y. All right, so go ahead and try number 59. And when you come back, we'll do it together. All right, we're back. So I'm going to change that fraction symbol to a division operation. That's perfectly legal in the world of mathematics. Then I'm going to use a ratio identity. I'm going to change cotangent theta to cosine theta over sine theta. And I'm going to change cosecant theta to 1 over sine theta. So I used a reciprocal identity and a ratio identity. You should know these identities pretty well by now, so you don't really have to, see these highlights. Okay, now we're going to change division to multiplication and flip. And we're going to multiply, and the signs are going to cancel out. There's one sign in the bottom, one sign on the top. And so we're left with cosine theta times 1, which is just cosine theta. So if you got that one right, excellent. All right, we're going to try one more of these problems that requires the ratio identities and the reciprocal identities. Try number 60. When you come back, we'll do it together. All right, we're back, so I'm going to convert that fraction symbol to a division operation. And then I'm going to use a reciprocal identity. Actually, 2 reciprocal identities. And then I'm going to divide. When you divide a fraction, you change to multiplication and flip the divisor. So now we can multiply, and we get cosine theta over sine theta, which is equal to cotangent theta. So if you got that one right, excellent. So I used a ratio identity, and I used reciprocal identities. Okay, so now we're going to do problems that employ the Pythagorean identities and the reciprocal identities. So we're combining these two. So sine squared plus cosine squared is 1. We used a Pythagorean identity. And 1 over secant theta is cosine theta. So in that case, we used a reciprocal identity. Tangent squared plus 1, that's a Pythagorean identity. That's equal to secant squared theta. And 1 over secant squared is equal to cosine squared theta. That is a reciprocal identity. Tangent squared theta plus 1, that's equal to, again, secant squared theta. Again, that's a Pythagorean identity. And secant squared theta is equal to 1 over cosine squared theta. That's a reciprocal identity. Multiply those together, and we get cosine squared theta over cosine squared theta. You don't have to show this step. You can go straight from here to the final answer, which is 1. And let's try one more of these before you try one on your own. Sine squared b plus cosine squared b, of course, is 1. And 1 over cosine squared is sine squared. So again, we're using the Pythagorean identities, and we're using the reciprocal identities. Okay, so you can take a look at these problems, get a picture with your phone. These will help you do these problems here. So try number 65, and when you come back, we'll do it together. All right, we're back. So sine squared theta plus cosine squared theta is 1. 1 over cosecant theta is sine theta. So we got that right. Good. Try number 66, and when you come back, we'll do it together. Okay, we're back. 1 plus cotangent squared theta is cosecant squared theta. That's a Pythagorean identity. And 1 over cosecant squared theta is sine squared theta. That was a reciprocal identity. If you got that right, good. Go ahead and try number 67, and when you come back, we'll do it together. Okay, we're back. One plus cotangent squared beta is cosecant squared beta. That's a Pythagorean identity. And cosecant squared beta is 1 over sine squared beta. That's a reciprocal identity. Multiply those and we get sine squared beta over sine squared beta, which obviously is 1. So if you got that right, good. Again, you don't have to write this step if you don't want to. Try number 68. When you come back, we'll do it together. All right, we're back. Cosine squared a plus sine squared a is equal to 1. Now, I probably should have clarified. Sine squared plus cosine squared is the same thing as cosine squared plus sine squared. Notice that the terms are rearranged here. That's okay. It doesn't really make any difference because of the commutative rule of addition. X plus y is the same thing as y plus x. 1 over cotangent squared a is equal to tangent squared a. Okay, so that is the reciprocal identity. All right, we're going to do a few more problems here that employ the Pythagorean identities and the reciprocal identities. So notice that we have a sine squared and a cosine squared, but they're separated. It doesn't really matter that they're separated. They both combine to 1. But let's put those together. So all I did was just move that cosine squared. I moved it over. I moved it to the left. So I took this cosine squared theta and I moved it over here. And now you can clearly see that we have a Pythagorean identity that is equal to 1. We also need to use, well, to make things simple, we could actually change sine to 1 over cosecant theta. So I'm using a reciprocal identity there. So sine squared theta plus cosine squared theta turned into 1. And when you multiply these, you get cosecant squared theta over cosecant theta. And when you divide those, we're just going to use the exponent rule number 2. You just subtract the powers. Another way to think about that is you have cosecant theta times cosecant theta over cosecant theta. So 2 of them cancel out, you're left with 1. All right, so there you go. That's as simple as we can make it. Let's try another one of these before you try one on your own. I'm going to write these purple terms next to each other. They're separated, but I'm going to write them next to each other. And when I do that, you can clearly see that that is a Pythagorean identity, the terms on the left. So these terms here turn into cosecant squared theta. And I'm going to use a reciprocal identity. So I turn that cotangent theta into 1 over tangent theta. And when we multiply, we get tangent squared theta over tangent theta. And then we get cosecant squared theta plus tangent theta. And that's pretty much as good as we can do. So we have the sum of 2 terms, but that's a lot better than the sum of 3 terms, and one of the terms is a product of 2 different trigonometric functions. So we simplified a little bit there. Okay, so go ahead and try number 71, and when you come back, we'll do it together. All right, we're back. So we have a cosine squared A, and we have a sine squared A that we're going to put next to each other. And that's a Pythagorean identity. Those just become 1. And I'm going to change secant A to 1 over cosine A. If we combine these, we get 3. And over here we have cosine squared A over cosine A. So we get 3 minus cosine A. So if you got that one right, good job. Okay, go ahead and try number 72. And when you come back, we'll do it together. Okay, we're back. So we have tangent squared omega plus 1. I'm going to put those next to each other. And why did I do that? I did it because this is a Pythagorean identity. So that turns into secant squared omega. And I'm going to change that cosine to 1 over secant omega. And you can do multiple steps at once, by the way. I'm just showing each step because I don't want to. Well, it's just easier to understand if you do it step by step. When you get into upper math courses, you're going to do multiple steps at once. Okay, so now we have secant cubed omega over secant omega. And that becomes secant squared omega. And notice that those secants cancel out, because we have a positive secant squared omega and a negative secant squared omega. So we are left with sine omega. So there you go. If you got that right, excellent. Okay, so we combined the reciprocal identities and the ratio identities, and then we combined the Pythagorean identities and the reciprocal identities. Well, now we're going to combine the Pythagorean and ratio identities. So we are starting off really slow with these identities because, again, we're trying to accomplish two things. Number one, we're memorizing these identities. You're doing so many problems that you are being forced to memorize the identities. That's the point. You're also understanding how these identities are used in expressions. You're going to see this all over the place in upper mathematics and science courses, especially physics. So, cosine squared b over sine squared b is cotangent squared b. So that was a ratio identity. 1 plus cotangent squared b is cosecant squared b. How do I know that? Well, that was a Pythagorean identity. So that whole thing was a Pythagorean identity. Okay, so we have ones here, and I'm going to do something that we've done already. I'm going to change that 1 to sine squared alpha plus cosine squared alpha. So I turn this 1 here into this. And I'm going to change the bottom one into the same thing. Now, a lot of students would try to cancel these out. Don't do that. You cannot cancel those because they're not factors of the numerator, and it's not a factor of the denominator. You can cancel out if it's a factor. It's not a factor. It's a sum. But we see that we have a cosine squared alpha and a negative cosine squared alpha, so those are going to cancel out. And we're left with sine squared alpha over cosine squared alpha. And of course that equals tangent squared alpha. We used a ratio identity. So I want you to try number 75, and when you come back, we'll do it together. Okay, we're back. So sine squared a over cosine squared a is tangent squared a. That was a ratio identity. Tangent squared a plus 1 is secant squared a. That was a Pythagorean identity. If you got that right, good job. Try number 76, and when you come back, we'll do it together. All right, we're back. So I'm going to change 1 to sine squared theta plus cosine squared theta. Same thing in the denominator. I'm going to change 1 to sine squared theta plus cosine squared theta. So I change this 1 to that, and I change this 1 here to that. And the sine squareds cancel out in the numerator, and the cosine squareds cancel out in the denominator. And then we get cotangent squared theta using a ratio identity. So if you got that right, excellent. Okay, so let's do a slightly more difficult problem. Again, we're using the Pythagorean identities and the ratio identities to solve these problems. So secant squared beta is equal to tangent squared beta plus 1. How do I know that? Well, that's one of your purple Pythagorean identities. And you can see that a lot of things are now going to cancel out because I changed secant squared to tangent squared plus 1. In the denominator, we have cotangent squared plus 1, and it's not really in the right order. We're used to seeing this as 1 plus cotangent squared beta, but the commutative rule of addition tells us that it doesn't really matter. So I'm going to change that. Maybe I should make that a different color. I'm going to change that to cosecant squared beta. So again, these are Pythagorean identities we're using. And notice that we have a positive tangent square beta and a negative tangent square beta. We also have a positive 1 and a negative 1, so those all cancel out. The only thing that remains is this cosine beta in the numerator. And in the denominator, our cosecant squared betas, they cancel out. And we're left with sine beta. So now we're going to use a ratio identity, and we get cotangent beta. So that was a little, wasn't really difficult, but it was a little more intimidating. Okay, go ahead and try number 78, and when you come back, we'll do it together. Go ahead and try number 78. When you come back, we'll do it together. Okay, we're back. Cosine squared alpha plus sine squared alpha is 1. So that was a Pythagorean identity. And we know that secant squared alpha is tangent squared alpha plus 1. So in the numerator, the 1's cancel out, and we're left with sine alpha. And you see these 1's here, they cancel out. And the tangent squareds, they cancel out, so we're left with cosine alpha. And sine alpha over cosine alpha, of course, is tangent alpha. So if you got that one right, perfect. Okay, now we're going to use all three types of the basic identities to simplify expressions. So cosecant squared theta is 1 over sine squared theta. That is a reciprocal identity. And tangent squared theta is sine squared theta over cosine squared theta. So that is a ratio identity. Now when we multiply these, we get sine squared theta over sine squared theta times cosine squared theta. You don't really need to show this step here. Once you realize that there's a sine squared theta and a cosine, or a sine squared theta on the top and a sine squared theta on the bottom, you can just cancel those out. But I'm showing that just to be thorough. So they cancel out, and we have -1 plus 1 over cosine squared theta. Now, why is that cosine squared theta in the bottom? Well, because it already was in the bottom. It's not going to go to the top for no reason. Sine squared theta divided by sine squared theta is 1. So we get 1 there. And 1 over cosine squared theta, we're going to, that's another reciprocal identity. So that is equal to secant squared theta. And secant squared theta is tangent squared theta plus 1. So we took that. That's a Pythagorean identity. We turned it into that. But notice that the 1's cancel out and you're left with tangent squared theta. So we simplified this expression up here all the way to tangent squared theta. Now, you should probably be aware that there are other ways to do that problem. You may find a different way that doesn't require all 3 types of the basic identities. But generally speaking, when people solve that or simplify that expression, they're going to probably use every type of trigonometric identity, or at least the basic ones. So let's try number 80. 1 plus cotangent squared omega, that is equal to cosecant squared omega. So that was a Pythagorean identity. 1 plus tangent squared omega is equal to secant squared omega, and that's another Pythagorean identity, but I'm going to use a different color. And notice that this is a little different from the identities that you have in front of you. The identity in front of you says that secant squared omega is equal to tangent squared omega plus 1, but it doesn't make any difference. The commutative rule of addition tells you that it's going to be the same thing. So now we're going to divide, and again, there's a lot of different ways to do this, but we're going to change that fraction symbol into a division symbol just to make things simple. There are faster ways to do these problems. You're going to learn faster ways. But now we are going to, well, we're going to use, let's go ahead and use the reciprocal identities. So cosecant squared omega is 1 over sine squared omega. And secant squared omega is 1 over cosine squared omega. So we used reciprocal identities there. So now we're actually going to divide. So we're going to change that division symbol to multiplication and flip the divisor, because that's just how you divide. Now we're going to change it to a multiplication problem. We're multiplying these fractions. We multiply straight across, and we get cosine squared omega over sine squared omega. And now you can see that this is turning into a ratio identity. Cosine squared omega over sine squared omega is cotangent squared omega. So we converted that complicated expression up there to something that is much, much easier to, well, it's much easier to write. So I want you to get a picture of these two problems. And I want you to attempt number 81. And when you come back, we'll do it together. Okay, we're back. So I'm going to use a reciprocal identity. So that was a reciprocal identity. And I'm going to use a ratio identity. So that turns into cosine squared theta over sine squared theta. And when we multiply, you don't have to show this step, but when we multiply, we get cosine squared theta over cosine squared theta times sine squared theta. Should probably draw those exponents a little better than that. It's very important that your work is neat. I don't have the best writing, but obviously people need to be able to see the numbers. So make sure that your writing is legible. All right, 1 over sine squared theta minus 1. Because these cotangents cancel out, or excuse me, the cosines cancel out. And now we're going to use another reciprocal identity. 1 over sine squared is equal to cosecant squared theta. But if you recall, cosecant squared theta is equal to 1 plus cotangent squared theta. So I used a Pythagorean identity, and the 1's cancel out, and we're left with cotangent squared theta. So if you got that one right, very good, excellent. All right, try number 82, and when you come back, we'll do it together. All right, we're back. Tangent squared x plus 1 is equal to secant squared x. That is one of our Pythagorean identities. 1 plus cotangent squared x is equal to cosecant squared x. So I'm going to use a different color for that. And now we're going to change that fraction to a division problem. Remember, the fraction symbol can be interpreted as a division operation. So now we're going to change secant squared to 1 over cosine squared, and cosecant squared to 1 over sine squared. So we used reciprocal identities, and now we're actually going to divide. So remember, when you divide fractions, you change to multiplication, and you flip the divisor. And so now we're going to multiply. And when you multiply fractions, you just multiply the numerators across. 1 times sine squared is equal to sine squared. And cosine squared times 1 is cosine squared. And now we're going to use a ratio identity. Sine squared over cosine squared is equal to tangent squared. So there you go. If you got that right, perfect. If you got stuck, that's okay. But that is the answer for 82. So that was the class today. So let's take screenshots of all the work that we did to help you with your homework or to study for tests. Here's screenshot number 1. And number 2. And number 3. And number 4. Number 5. Number 6. Number 7. Number 8. Number 9, number 10, number 11, number 12, and number 13. But don't go before you get your homework. Let's look at the homework. There's 20 problems for the homework. And you see that you have the answers written next to each problem. Be sure that you show the steps. You need to provide the space for each problem to show the steps. You're going to have to rewrite each problem and show the work. So get that homework done completely, correctly, neatly, and put it in order in your binder. And I'll look forward to seeing you in the next class.